Welcome. In this video we are going to discuss about ion exchange chromatography. Now we use this ion exchange chromatography for the separation of charged molecules. If you want to separate charged molecules, then you will use the ion exchange chromatography. You will apply ion exchange chromatography to those charged molecules so that they can be separated. Now in this technique, in this ion exchange chromatography, the ionic solutes display a reversible electrostatic interactions with the charged stationary phase. Okay, the ionic solutes display reversible electrostatic interactions with the charged stationary phase. Now the stationary solid phase which is used in this ion exchange chromatography is made up of an insoluble matrix to which there is covalent attachment of cations and anions, which are known as ion exchanger. Okay, so this ion exchangers, this cations and anions, when they are covalently attached to an insoluble matrix, then that is your stationary solid phase. Now the solutes which will enter this column which has the stationary phase, those solutes can be negative, they can be positively charged, or they can be neutral. Okay, negatively charged, positively charged or neutral solutes will enter the column which we are using in ion exchange chromatography, and whether the solute will be positively charged or negatively charged or neutral, that will depend upon the experimental conditions. Now the solutes of opposite charges which are present in the mobile liquid phase, these solutes of opposite charges will bind reversibly with the ion exchanger, and this binding will be through electrostatic interactions. Okay, solute ions which have opposite charge with respect to ion exchanger, those solute ions will bind reversibly, and this binding with the ion exchanger, this reversible binding, will be through electrostatic interaction. Now the strength of this interaction, okay, the strength of this interaction between the solute ions and the ion exchanger will depend upon the size of the charge and charge density of the solute. Okay, it will depend upon the amount of charge per unit volume of solute. Okay, this strength of interaction. Now greater the charge or charge density, the stronger will be the interaction with the solute ions and the stationary phase. And the thing is that the neutral solute show a little or no affinity towards the stationary phase, as they are neutral and they move with the eluting buffer. Now the bound solutes, okay, the solutes which are bound to the stationary phase, those bound solutes can be released by eluting the column with a buffer which has increased ionic strength or increased pH. Okay, so the molecules have bound to the stationary phase, and now you have to release those molecules. And how will you do that? Well, you will elute the column with a buffer which has increased ionic strength and pH. So the increase in the buffer ionic strength will release the bound solutes by displacement. Okay, so you just increase the ionic strength of the buffer to release the bound solutes. When you increase the buffer pH, okay, for the release of the bound solute, the increase in the buffer pH decreases the strength of the interaction by reducing the charge on the solute or on the resin. Okay, the solute and resins are charged molecules. If you increase the pH, then there will be reduction in their charges. And if there is a reduction in the charges of solute and resins, then this will cause a decrease in the strength of the interaction between them. And that is how you release the bound solutes during ion exchange chromatography. Now let's talk about ion exchanger. Now this ion exchangers are made up of two parts. The first is insoluble matrix and the second one is the chemically bonded charged groups which are present within or on the surface of the matrix. Okay, so ion exchanger, you have insoluble matrix, and on or within that matrix you have these charged groups, and there is chemical bonding between this charged group and this insoluble matrix. Okay, that is what your ion exchanger is. Now this ion exchanger can be cationic exchanger and anionic exchanger. Okay, cation exchanger and anion exchanger are the two types of the ion exchanger. Now this cation exchanger is also known as acidic ion exchanger, and it is used for the separation of cations, whereas this anion exchanger is known as basic ion exchanger, and this anion exchanger is used for the separation of anions. Now each type of exchanger is also classified as strong or weak. Okay, you can call a strong exchanger or a weak exchanger, and this classification is based on the ionizing strength of the functional group of that exchanger. Okay, so there is classification such as strong ion exchanger or weak ion exchanger, and that classification depends on the ionizing strength of the functional group. For example, consider an exchanger, okay, which has quaternary amino group. Now that exchanger, because of this quaternary amino group, is said to be a strongly basic anion exchanger. Okay, why this exchanger is strong anion exchanger? Well, because it has this quaternary amino group, okay, as the functional group. That's why it is strong. So it depends on the functional group. Okay, consider this. Okay, if an exchanger is having primary or secondary aromatic or aliphatic amino groups as the functional group, then that exchanger will be a weakly basic anion exchanger. Okay, if there is presence of this primary or secondary aromatic or aliphatic amino groups, then it will be a weak anion exchanger, and if there is presence of this quaternary amino group as functional group in the exchanger, then that exchanger will be strongly anionic. Okay, that we will call that as a strongly anionic exchanger. So we discussed about anionic exchanger. What about cation exchanger? Well, a strongly acidic cation exchanger will have sulfonic acid group as its functional group. Okay, if in any exchanger there is presence of this sulfonic acid group as the functional group, then that exchanger will be strong cation exchanger, a strongly acidic cation exchanger. So consider this. Okay, this is the bead. Okay, this is your matrix, and to that matrix this functional group is attached. Now this functional group is known as DEAE, and because of the presence of this functional group, this ion exchanger becomes an ion exchanger. Okay, because as you can see there is a positive charge here. Okay, so That is the reason why it will bind to the negatively charged molecules. That is, it will bind to anions. Okay, so that is the reason why, because of this functional group present here, this ion exchanger is an ion exchanger. And consider this case. Okay, this is a bead, and to that bead this functional group is attached. Now this functional group is known as carboxymethyl functional group. Okay, and as you can see, there is the presence of negative charge on this group. Okay, so that is the reason why it will bind to positively charged molecules, and that is the reason why it will bind the cations, and that is the reason why this whole thing is known as cation exchanger. Now let's have a look about the commonly used ion exchanger. Okay, so this is the example of an ion exchanger, that is DEAE cellulose, and it is a weakly basic ion exchanger. Okay, weakly basic anion exchanger, and the functional group which is there in this DEAE cellulose is diethyl aminoethyl. Okay, this functional group is there in your DEAE cellulose. And then this QAE cephadics is another anionic exchanger, and in this anion exchanger, this QEAE cephadics is a strongly basic anion exchanger. Okay, this was weak, DEAE was weak, this QAE is strong, and the functional group which is there in this QAE cephadics is quaternary aminoethyl, and this is also an anion exchanger which is known as Q-cepharose. This is a strongly basic anion exchanger, and it has a quaternary ammonium as its functional group. Now let's look at cation exchanger. Okay, now the example of the cation exchanger that we are considering here is CM cellulose, then SP cepharose, then sucrose S. Okay, these all are the commonly used cation exchangers. Now considering CM cellulose, it is a weakly acidic cation exchanger, and it has carboxymethyl as the functional group. Then SP cepharose is a strongly acidic cation exchanger, and it has sulfopropyl functional group. And at last we have this sucrose S cation exchanger, which is a strongly acidic cation exchanger, and it has methyl sulfate as its functional group. Now the solute in a given sample which has an opposite charge with respect to the charged group of the ion exchanger will bind to the column. Okay, if the solute has the opposite charge with respect to the charged group present on the ion exchanger, then that solute will bind to the column. Now the separation of charged solute happens in the ion exchange chromatography because different solutes have different degree of interaction with the ion exchanger. Okay, different solutes have different degree of interaction with the ion exchanger, and the reason behind this different degrees of interaction with the ion exchanger is the differences between their charges, their charge density, and the distribution of charges on the surfaces. Okay, so because of these differences, there is different degrees that the different solutes show different degree of interaction with the ion exchanger, and because of this there is separation of the charged solutes. Now consider a solute. That solute has net positive charge at the pH 7. Now this solute will bind with the ion exchanger which has carboxylate group as its functional group. Now why this is happening? Because this carboxylate group is negatively charged. The solute is positively charged. So that is the reason why it will bind. And this ion exchanger which has this negatively charged carboxylate group, this ion exchanger is the cation exchanger. Okay. And if in the system there is the presence of negatively charged protein, then this negatively charged protein will not bind to this ion exchanger. Why? Because the carboxylate group is negatively charged, the protein is negatively charged, they will not bind, they will repel. Okay, so this is how the ion exchange chromatography works. So this is the diagram. Okay, let's see. Now, okay, so you have a column, and on in the inner surface of that column you have immobilized cation surface. Okay, this is your stationary phase. Now that stationary phase is the matrix of that stationary phase have this positively charged groups attached to it, and that is the reason why the stationary phase is positive. Now you put a mixture of solute, okay, onto this column. Okay, now this mixture of solute will pass through the column. Now in this mixture of solutes, some solutes are positively charged, the other solutes are negatively charged. Now what will happen is that this negatively charged solutes will bind to the positive surfaces of the stationary phase, and the positively charged solutes will pass on, and that is how you separate the positively charged molecules from the negatively charged molecules. Okay, so this is your ion exchange chromatography. Another thing is that the positively charged molecule got eluted. Okay, now you have to elute this negatively charged molecules. Now how will you do that? Okay, they are bounded there. Okay, so let's see how you will do that. So those bound molecules can be eluted by altering the pH of eluting buffer or by increasing the salt concentration of the eluting buffer. Okay, so there are two ways by this bound molecules can be released. Either you increase the salt concentration of the eluting buffer, or you can alter the pH of the eluting buffer. Now this positively charged proteins that are bound to the cation exchanger can be eluted by increasing the salt concentration in the eluting buffer. And how this will happen? Well, the cations in the buffer, okay, now the eluting buffer you have salt concentration, so salt are there, that is the reason why there will be cations and anions. So the cations of this buffer will compete with this positively charged proteins to bind to the ion exchanger. Okay, ion exchanger. So let me just do it with the diagram. So this is your stationary phase. Okay, this is your column. Okay, this is your matrix. Now that matrix has negative charge, and that is the reason why this positively charged proteins were able to bind to it. Now you will put a buffer, and in that buffer you have positively charged cations again. Now this positively charged cation will bind to the matrix, okay, and that is the reason why they will compete with these proteins, and that is the reason why then these proteins will not be able to bind with the matrix and they will be eluted out. Okay, so that is what this statement is suggesting, that the cation in the buffer will compete with the positively charged groups of the protein to bind with the ion exchanger, and that is how the positively charged proteins will be eluted by increasing the salt concentration of the eluting buffer. So proteins which has low density of net positive charge will emerge first as compared to those molecules which have higher density of the net positive charge. Okay, so the more positively charged a protein is, it will remain in the matrix for a longer time. If a protein has less positive charge, then it will elute first. So that's all for this video. Thanks for watching. See you next time.